Welcome to the video on logarithms. Logs as we normally call them. And I wanted to start with a basic overview so that you understand the purpose of logs. And the purpose of logs actually begins in the time before there were calculators. Now that there's a calculator, if I wanted to multiply 117 million by 34 million, I would just type it in and I'd get the answer 3.978 quintillion is what I think that works out to be. And so in the old days, before the calculators, we had to do this with log tables. And all of your algebra books had a log table set in the back of the book. And what we would do is we would take, for instance, the log of 34. If we had to multiply these, the way we did this is we'd get the log of 34, which is 1.51. And that would mean that 10 raised to the 1.531 power would equal the 34, which was actually 33.96 if you calculated it out, but that's close enough for doing the kind of work we were doing. Log of 117 is equal to 2.068, and that meant that 10 raised to the 2.068 power would equal 117. It actually equals 116.94 and some other numbers. So now we're going to combine that with the 1 million and make it 34 million and 117 million. But to do that, we break apart the 1 million. Well, 1 million is 10 to the 6th power. Or if we said log of 1 million, it is 6, meaning that 10 raised to the 6th power is a billion. So the way logs work is we just had to add this. We added the 6 for the million to the 1.531, which was for 34. And that gave us 7.531. And what that meant was 10 raised to the 7.531 power equaled the 34 million approximately. We'd do the same thing with the next number, the 117 million, except we would take the 6 and add it to the 2.068, and that would give us 8.068. And then we add these two numbers together, and that gives us 15.599. Now, what that would mean is that 10 raised to the 15.599 was the answer to the problem. What's 117 million times 34 million? And so, aren't you glad you live in the days of the calculator where you don't have to worry about this? But the ACT still tests for this, and that's why we want to understand logs a little better. You can see that if we actually put this back into a calculator, we get 3.971, or 972 if you round the 9 up, quintillion, compared to the 3.978 quintillion. So it's accurate to the 4th decimal place. That was pretty close for what we'd be doing. So now let's take a look at how we put the log rules together that help us understand how to do this. There are some basic rules with logs. First of all, we'll start with this one. The log of x times y is equal to the log of x plus the log of y. The log of x divided by y is equal to the log of x minus the log of y. So remember, if it's multiplied, you add them. If it's divided, you subtract. The log of x raised to the y power is equal to y log of x. And taking the y root of x is going to be, like if you take the cube root or the 4th root, it is simply the log of that number divided by y. Okay, now let's take a look at how we use these. On this next page, I have kept the log rules up in the corner so we can look at it and see. The way we write these out is log to the base 10. Now, if a base is not here, then that means it is to the base 10. We don't usually write the 10, but I wanted to show you. It could say log to the base 5, and we'll look at some of those in a few minutes. So now if I take this one, log of b squared c, what that's going to be is we would say, using these rules over here, that this is going to be the log of a plus put the 2 in front, log of b. Now, why did we put the 2 in front? Remember, if I have log to the of x to the y power, I move the y in front. So I did that on the b. Now these two are multiplied together, so I added them. Now we're going to subtract log of c. And that gives us this full expression for the answer. In our next example, what we have is the log of to the base w, whatever our base is, but it's that same number to the 6th power divided by that same number to the 4th power. So since they're divided, we're going to use the subtraction rule and get log to the base w of w to the 6th minus log to the base w of w to the 4th power. Well, here's what we have to remember is we'll sort of take a detour down here. If I take log to the base 10 of 100, it equals 2. That means that 10 squared equals 100. Well, it would also mean if I did this, log to the base 10 of 10 squared would simply be 2. Keeping this in mind, we look up here, log to the base w of w to the 6th is just going to be 6. Minus log to the base w of w to the 4th is 4. 6 minus 4 would equal 2. And that's an example that's been from a former ACT test. They did one similar to this. We have another problem here to look at some of this about the bases. If I take log to the base 5 of x equals 3, what that means is that this 5, my base, raised to the 3rd power is equal to x. So 5 cubed is equal to 125. I would look at it another way, and I could say log to the base x. I don't know the base, but that number of 64 would equal 3. What that means is the x cubed equals 64, and of course 4 cubed is 64. The next one we'll look at is log to the base 3 of 81 equals x. What that means is 3 raised to the x power equals 81, so our x is equal to 4. Log to the base 10 of x equals 3 means 10 cubed equals 1,000. So that gives you a little bit of an example of how this works with the numbers as well. Now we got a couple of sample problems to look at. And it says, solve this for x. Log to the base 2 of x equals 5. Well, what that means is 2 raised to the 5th power is equal to x. Well, 2 to the 5th power is 32. That makes the answer C. Now we'll look at this next one. Solve for x. Log to base 5 of 3x minus 4 is equal to 2. And in this case, with as much work as we've already done, I think we need to let you have a minute to do this. So we're going to say, we're going to give you about 30 seconds, and you may begin. Now, 30 seconds may not have been enough time for you to figure this out. Let's take a look. What you have is the first step is the 3x minus 4 equals 5, which is the base, to the 2nd power squared, which is 25. So now our problem is 3x equals 29. Add the 4 to the 25 and get 29. So now all we have to do is divide the 29 by 3 and get x is equal to 29 over 3, making B the correct answer. Okay? So on this one, we're going to do a base change, and it says evaluate log to the base 2 of 8. Okay? So take about 20 seconds. This one shouldn't take long, and let's see what you come up with. Let's. What this says is log to the base 2 of 8, and what it means basically is we could say 2 to what power equals 8, and that would make x equal to 3. They're doing it log to the of 8 divided by log of 2 is going to give me 3. And that gives us the answer B. Look at our next problem. And this one is a little bit confusing, but I want you to take a second and look at it, and then we'll talk through it. 10 to the log to the base 10 of x equals 100. Now you think about what we've been going over and see if you can figure this one out. Okay, we won't let you work on that too long if you get confused with it. What it means is that 10 to the second power is 100. And so if I take the log to the base 10 of x is equal to 2, that means 10 squared is 100, and 100 is equal to x. And so that means that the answer for x in the middle here is 100. Log to the base 10 of 100 would be a 2. So 10 squared would equal 100 here. So that makes the answer in the middle there A. This is our next problem, and I want you to just solve this one for positive values of x. When you come down to your answer, you'll have a choice of it being positive or negative. So we just want to look at the positive value. So take about 20 seconds on that one, and we'll see what you get. Okay, we had a little extra time on that one. Let's take a look. So our first thing is that log of, we've rewritten the problem now to get log of x squared divided by 16. Remember that minus sign means these two were divided. So log of x squared divided by 16 is equal to 2. So what that tells us is x squared over 16 has to equal 10 squared. Well, 10 squared is 100. And then we take the 16 times 100 here. I'll write this out. We get 16 times the 100 is 1600. So now we have our x squared is equal to 1600, what you see here. And for x squared to equal 1600, then x would have to equal 40 because 40 squared is equal to 1600. It could also equal negative 40, but I put it into question here. We're only looking for the positive values, so that would make C the correct answer. Otherwise, we'd have to allow for two correct answers because we have a negative 40 as a choice as well. This one is expanding logarithmic expressions, and this is something we've done a couple of already, so I think you should be kind of fast with this. Let's go for 20 seconds, and you may begin. All right. So the answer to this one is just going to be pretty simple. We take the 2 on the A and put it in front, and we get log of A. But since these were multiplied, we simply add them. 2 log A plus log of B, making the correct answer B. Now our next one, log to the base 2 of 64 over x equals 3. Let's see what you do on this one. this one worked out. What we have is the 64 over x is equal to 2 cubed. We take the 2 and cube it. That's what this is equal to. And that is going to be equal to 8 because 2 cubed is 8. So therefore, x has to be 8 because 64 divided by 8 equals 8, making A the answer to this one. Now we're going to look at some word problems, and we're going to sort of help you get started with this. We've got some other information in here because this is a problem that is similar to one that we've had on an ACT test. Investing $500 at 4% interest, how long will it take to get to $1,000? Well, if you remember your future value, or in this case they call it A, which is the amount of money that's accumulated, okay, A is equal to P times 1 plus R over N, close parenthesis, raised to the NT. Well, the N and the T multiply together to give us our number of terms. The T is in years, and the N is the number of compounded times we have per year. If it was quarterly, it would be 4. If it's monthly, it would be 12. If it's daily, it would be 365. Okay, so now we're going to rearrange the formula to solve for T on this one. So you've got T is equal to the log of A over P divided by N log of 1 over R plus N. And then they give you all the numbers here. So let's take just a minute and let you work on this one, and let's see what you get. What our next one is, in this particular problem, the future value of a amount of money deposited at an interest rate is equal to the present value times 1 plus the interest rate divided by the number of terms that is compounded over, raised to the number of terms that we're dealing with on this. And so this would be like, okay, just to give you a quick example before you start working on it so that you can look at it from a log standpoint. If I wanted the future value of $1,000 deposited at 1 plus, and let's say our interest rate is 6%, that'd be 0.06 in decimal form, divided by, and we're going to compound it monthly, okay? So that's going to be divided by 12, raised to, and if we wanted it for 4 years, that would be 48 months. Okay, so this is how the equation would go if we knew the number of terms. But what this is doing, and what the problem is wanting you to do, is let's assume that you knew that it was going to go to $2,000 is equal to $1,000 times 1 plus, what would the interest, it would have an interest rate 0.06 over the 12, and now we want the number of terms. Well, you can see that since it's an exponent, this would be a log function. You'd take the log of both sides and you could solve for it. So what we've done is set this up, and you've got an A of 1,000, which would be the future value, and then you got the 500, the present value, the interest rate, and the number of terms. So you want to solve for T using that formula. All right, so let's take a look and see how that works out. Okay, so we're going to step forward and see what we come up with here. And in this case, the way that we would do this is we got the equation set up like we were looking at, and it would be log. It's going to be where T is equal to the log of A over P divided by N log of 1 plus R over N. Now, how did we get that? Well, if we take the equation that we have here, A is equal to P times 1 plus R over N raised to the NT powers. What we would do is first divide the P over. So now we're going to have an A over P is equal to parenthesis 1 plus R over N raised to the NT power. All we really want is that one number. So what we would do is take the log of both sides. Now, why would we do this? Okay, we're going to do this because remember, if we have a log of something to an exponent, we simply move the exponent in front. And so now what that's going to do is give me log of A over P is equal to NT times log of 1 plus R over N. Well, what I really want is T in years. And so I'm going to divide everything else over. I'm going to divide this side by N and log of 1 plus R over N. And I divide this side by it, and I'm going to get N log. And all we have to do was solve this out after we get the equation right, R over N. Now, our T, if we'll just put it on the left, is equal to the log of 1,000 over 500 divided by N log, and our N is 12. So we're going to back up and make that a 12, since we have that number. 12 times log of 1 plus, now my interest rate's 0.04, over, and my N is 12 again. And this is going to give me the T. So we'll put this in. This is going to become in the top log of 2 divided by, and here I've got the 12 log of 0.04 divided by 12 plus 1. So let's get that number. So this is going to give me log of, and what I had was 0.04 divided by 12 is equal to 0.00333. Now we add 1 to that, and I get 0.00333. Well, the log of that is to base 10, which is what we're looking for here, is going to be 0.001445, and that's enough, times 12, and that will give us 0.017. So all of my bottom resolves to a 0.0173. That's good enough. And now I get the log of 2. So if I take a 2 and hit the log button, I get 0.301. Well, 0.301 divided by 0.0173 comes out to be 17.4. And so that means she's going to have to wait 18 months to get that, to get her money back. She's going to take 18 years at 4% for it to double. 18 years. It says 18 months, but it should be 18 years because we were solving for years. Okay, now we'll take just a minute and go over this one in a little bit more detail. Here's what we did to get to the part that we're started with here. We take this is the formula they came up with, but we're going to start with this one because I want you to see how you do it, because on the ACT, they're not going to give you this formula to start with. So the first thing I did is divide the A by the P. Move the P from this side. So I get log. Well, first of all, I had A divided by P is equal to 1 plus R over N raised to the NT period, number of periods. And so what I wanted to do is find out what the exponent is, remembering that our rule is that if I have a number with an exponent, like if I have log to the base A of x to the y power, the y goes in front, log to the base A of x. And that's what I want. So what we're going to do is rearrange this formula. I take the log of both sides, and then I'm going to divide this log of 1 plus R over N over to the other side. And I end up with their formula. Now that I end up with their formula, I am able to put the numbers in. So t is equal to log of 100 divided by 500, which is what I want, divided by what I'm starting with, divided by 12, we're going to say compounded monthly, times the log of 1 plus 0.04 over 12, close parenthesis. Well, when we do this, we're going to come down to 1,000 divided by 500 is 2. So we're getting the log of 2, which is 0.301. Then we're going to do 12 times the log of 1.00338, I think that is, and that is going to give us the number, and it's this one divided by 12, so that's going to give us 0.0173. So when you divide this out, you get 17.4, which means it's going to take us about 18 years. If we started with $500, it earned 4% compounded monthly, and we want to know when it's going to get to $1,000. It takes us about 17 years. Okay, so now let's look at the next problem that we've got. We've got a couple more like this. So starting with this one is about population growth. And it says a certain species of fish in a lake is expected to grow according to a continuous exponential growth model with a growth rate of 5% per year. If the current population is 2,000 fish, how many years will it take for the population to reach 3,000 fish? And they give us this formula. A is equal to P, and then this letter E raised to the RT power. And then they tell us what it is. A is the amount of time, the P is the initial amount, R is the rate of growth, and T is the time in years. Okay, so let's take about, now that we've done one, let's take about 30 seconds and see how you do on this one. Okay, so let's take a look at this one. Doing this, what we're going to do is plugging in the numbers on this, taking the log of A slash P, we get 1.5. Okay, that's the 3,000 divided by the 2,000, so we're getting that. And then in the bottom, we've got this 0.05, which is the interest rate. And when you plug the numbers in, just like we did here, and hit it on your calculator, you're going to get 8.1 years. It'll take about 8.11 years for it to reach 3,000. Now we have our last problem, and this is one about radioactive decay. This is losing. Instead of growing, this is losing. It is decaying at the rate of 3% a year. If the initial mass is 100 grams, how long will it take it to get down to 50 grams? And so they use that same formula here, except it's with a minus in the exponent. So work on that one for a minute. Let's give you about 35 seconds and see what you come up with. Okay. So, just like we have already done in the two previous ones, you're just going to plug in the numbers where the A was 50 and the P was 100. And then your R is 0.03. And when you plug those in to the equation, you should have gotten something like 23.1 years, or since we're only dealing with whole numbers for the answers, it would have been 23 years. So hopefully you have a better understanding about logs now, and multiple ways that they can be used to get the exponent of something where we're looking for it, other than trial and error, which is what you might do most of the time. So hopefully this helps you understand logs a little bit better. Thanks for watching.